All right, week 9 tutorial. Let's start with the matrix iteration method. I will start with question 1. We'll do just this one. This one is very similar. You do this on your own. I'll just do this first one, which is a rotational system that we didn't do in class. So we'll do it now in the tutorial. So determine the stiffness and flexibility matrices for the systems shown in figures 1 and 2. So we'll just do figure 1. And then says, use matrix iteration to find the lowest and highest natural frequencies and the associated mode shapes. So I'll take this aside. So this is for transverse vibrational beams. But this thing is about matrix iteration method. Okay, what do you remember about the matrix iteration method? There are two equations. We'll spell them out later because the first part of the question says find the stiffness and flexibility matrices of this particular system. So let me draw the system first. This is a fixed support at the top. Now we have something here with a certain rotational mass. Then we have another one and another rotational mass. Then we have the last one also with some rotational mass. Now this system here has stiffnesses of 3K, 2K, and K, and 3, 2, 1. So 3, 2, 1, 3, 2, 1. 3K, 2K, and K. And this is 3I, 2I, and just I. So step 1, so we want to find H, the flexibility matrix, and we want to find K, which is the stiffness matrix. Now, to find K, you know, it's very easy. You do the free body diagram, then you look at the equations of motion. For the flexibility matrix is arguably even easier because you don't need the equations of motion. It's all about Hooke's law. So if you remember, Hooke's law is F equals Kx. And so that means that X equals HF. Because remember, the relationship between K and H is that K is the inverse of H. And so consequentially, H is the inverse of K. So that means that we can use, let's say, if I apply, remember, in order to find the displacement, if apply one force, F1 is a unit force, and then you have F2 equal F3 equals 0. This is exactly the direct stiffness method, but the other way around. Remember, the direct stiffness method is apply unit displacement and find the set of forces that make those displacements happen. Whereas in this case, we are doing the other way around. We apply unit force and we see what are the displacements associated. This will give us the compliance of the system, and all the compliances give the flexibility matrix, also called the compliance matrix, exactly for the same reason. So if I apply a force of 1 and F2, F3 is 0, so if you look at it, I end up with, let me do the free body diagram of this. Sorry. Oh, what's going on with that? So if I apply, well, in this case, the force is a moment. So if I apply a torque, say in this direction of 1, then this will respond with 3k times θ1. And let me put here θ1. The 3 degrees of freedom I have here are θ1, θ2, and θ3. So if I apply a torque of 1, then this will respond with 3k θ1 opposite, and this will also respond with 2k θ1 minus θ2 opposite. So I can look at it and see that the equation is 3k θ1, so minus 3k θ1 plus 1 minus 2k θ1 plus, well, let's leave it like this, 2 minus 2k θ1 minus θ2 equals 0. Because this is statics. We're not talking about dynamics here. We are just using the statics equation, this one. Is force and displacement. The displacement is this, θ1, θ2, and the force is 1. In this case, we're talking about rotational displacements, so angular displacements, and rotational forces, which are moments, effectively. If I do the same for the other mass, so if I do the same for the other mass, I get, of course, here, I don't have this force anymore. I am applying the first force only, force 1. So the second mass doesn't feel the external force, but it feels this reaction, which is 2k θ2 minus θ1, and this one, which is k θ2 minus θ3. And these things must be equal to 0, because this is in equilibrium. So this is my equation 1. This is my equation 2, which is 2 minus 2k θ2 minus θ1 minus k θ2 minus θ3 equals 0. This is my second equation. And my last equation is this one. But here I don't have anything at the bottom. And this thing is not 2k, it's just k θ3 minus θ2. So this is the only force that is acting here. So that force must be 0. So minus k θ3 minus θ2 equals 0. This is my third equation. Now look what's going on here. This thing is 0. And so this thing is 0. Do you agree? This thing is this. This is this. Okay? So what I'm saying is that this is 0. Can you see it? And that means that this is 0. Can you see it? So how much is θ1? It's 1/3 of k. θ1 is 1/3 of k. And what does it mean for this to be 0? in how many ways this can be 0? Either k is 0 or θ3 is equal to θ2. So of course k is non-zero, because otherwise what's the point? So from this equation, from 3, I know that θ3 equals θ2. And then from 2, again, this is 0. So in how many ways this can be 0? Either k is 0, again, it's not the case. So θ2 must be equal to θ1. From 2, I get that θ2 equals θ1. And finally, from 1, I get that θ1 is 1 over 3k. And so this is θ2 is also 1 over 3k, and θ3 is also 1 over 3k. And there you go. This is the first column of the flexibility matrix. This is not very hard. You just have to find, again, it's the 3 equations and 3 unknowns. That's what it is. So my flexibility matrix H equals 3 by 3 and I just found it's 1 over k it's 1 over k times 1/3, 1/3, 1/3. I found my first column of my flexibility matrix. To find the second column of the flexibility matrix, you do exactly the same process all over again, but now your force is applied here. You have a unit force of the second mass and no force on the other mass. Then you find the second column, and then you find the third column. Now, is this complicated? Yes. So is there an easier way? Yes. What's the easier way? Well, you look at this. If you apply force here, then this one displaces 1 over 3k, and these two that are free to rotate with 1, the way they will displace by exactly the same amount. If I apply the torque here, 1, this one will follow this. This one will be 1 over 3k, because it's only attached to the mass at the top, to the spring at the top. And this one is two springs in series. Okay, that's very easy. So 2 springs in series means that this is 1 over 3. Springs in series, 1 over 3 plus 1 over 2. And the third one, we said, is exactly the same as the second one because it's free to move. For the last one, if I apply a force there, the last one is 1 over 3 plus 1 over 2 plus 1. The second one is 1 over 3 plus 1 over 2. And the first one is 1 over 3. So this is 1/3. 1/3 plus 1/2 is 1/3 plus 1/2 plus 1. This is the flexibility matrix of the system. Also, the stiffness matrix of the system, again, this should be K times. This, we can take it very easily by just looking at what we did so far. Now, ideally, you should do the equations of motion, look at the stiffness, look at the, this is how you do it properly. And if I ask you to do that at the exam, I want a couple of examples at least, okay? So if it's 4 masses, you do the first 2, and then you just complete the matrix, that's fine. But I want you to show me that you know how to find properly the stiffness of a system, because this thing that I'm doing by using the springs and things to fill the matrix directly, really only works for masses and springs. If it's a more complicated problem, it doesn't work anymore. But the equations of motion system always works. So this is the first mass is attached to 5K worth of springs. The second mass is attached to 3K worth of springs. And the last mass is attached to 1K worth of springs. In between 1 and 2, there is -2. In between 1 and 3, there is 0. And in between 2 and 3, there is -1. So this is the stiffness matrix of the system. We can check that. We can check that this is correct by showing that H-1 is K. You can do this with MATLAB. Okay, 100%, you get that H-1 is equal to K, or K-1 is equal to H. Again, it's the same thing. Yeah, okay, it doesn't matter. Okay, now that we have found the stiffness matrix and the mass matrix, sorry, the stiffness matrix of the system, what is the mass matrix of the system? It's very easy. It's 3 point masses, basically. It's 3I, 2I, and I. Since we labeled them in a certain way, we have that the mass matrix of the system is 3I, so I times, I take I as a subject, I get 3I, 2I, and I in a diagonal pattern, of course. So it's a diagonal mass matrix. Now, what do? We go back to the lecture slides and we look at the equation. So if you look at the equation, week 9. Why 6? Week 9. And you look at the two slides, sorry, the single slide I showed you, this one. So with this one, you find the highest, and with this one, you find the lowest. So 1, to find the highest natural frequency mode shape, and 2, to find the lowest natural frequency mode shape. So let me copy these ones. So this is the matrix iteration method. So for the formula sheet says that m-1 times k times x equals omega squared times x. This is the highest. And the other way around is k-1, which is h times m times x times the inverse of omega, which is 1 over omega squared times x. This is the lowest. Okay, I have them here now. So we start from the lowest. And so how do we estimate the lowest mode shape of this thing? Well, before doing any guesswork, let's find first this matrix, which is m-1 times k. So to find m-1 times k, I have to take m-1, which is 1 over I times 1/3, 1/2, and 1, 1/3. This is the inverse of the mass matrix. Very easy because it's the inverse of a diagonal matrix. Times k, which is k, I'll put it here, so it's k over I. And this is 5 minus 2, 0. So 5 is 2, 0, minus 2, 3, minus 1. And this is 0, minus 1, 1. Okay, this gives a matrix, which is The first element here is row times column. So it's 1/3 times 5 plus 0 times -2 plus 0 times 0. So this is 5/3. The second element here is first row, second column. So it's -2/3. And this is 0. For the second one, we have 0 times 5 plus 1/2 times -2 plus 0 times 0. So this is -1. This one is 3/2. And this one is -1/2. For the last one is exactly 0, -1, 1. Sorry, is it 1, 0? Yeah, so row times column, row times column, row times column. Yes, it's exactly the same. So you should agree with me that this is exactly, and I forgot, of course, k divided by I. Always important that you put k divided by I because they were taken out as a subject. Let me check with MATLAB if this is correct. So I'll take M, my mass matrix is, again, I will be not using K and I because they are just variables. So the mass matrix is 3, 2, 1. Of 3, 2, 1. The stiffness matrix is 5, -2, 0. -2, 3, -1, and 0, -1, 1. Okay. So I take the inverse of M, which of course is this one. The inverse of M times K is 1.667. Is this 5 divided by 3? 5 divided by 3. Yes. Okay, so it looks like negative, 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 negative. Yes, positive, positive. Yeah, that's correct. That's exactly what I got here. As you can see, two symmetric matrices. This is a symmetric matrix. This is a symmetric matrix. The result is not a symmetric matrix. This is non-symmetric. So be very aware that you should not be getting a symmetric matrix if you multiply two symmetric matrices together. That's not always the case. It is the case only if this diagonal matrix is the identity matrix or proportional to the identity matrix. Okay, now that we have this, we can start our lowest because we have h times m. Oh, I said highest and lowest. Well, I want to start with lowest, so I'll also calculate this now. I'll calculate HM because I want to start with the lowest frequency. And this is I divided by K, of course, because it's HM instead of M minus 1K. And this would be the flexibility matrix, which I'll just copy. Times the mass matrix equals. Now this I will do with MATLAB because it's much more complicated. Well, it's not much more complicated, but it's definitely more of a problem to do by hand. So this is K, so I'll find that H is the inverse of K. Now see, in this case, we must let MATLAB do the inverse of K because we need the numbers inside that inverse of K. See, that's exactly, see, 1/3, 1/3, 1/3, 1/3, 2/3, sorry, 1/3 plus 1/2, 1/3 plus 1/2, 1/3, 1/3 plus 1/2, 1 plus 1/3 plus 1/2. That's exactly what we had. Okay, so this is H times M, as I said, H times M gives this matrix here. Quite easy. So we have 1, 1, 1. Then we have 0.667 is 2/3. 2/3. And this is 1.67. 1.67. And this is 0.33, 0.83, and 1.83. Okay, I have them here. And now I can start. So I start with the lowest. So starting with lowest, that means I copy this thing. I have it here as a reference. So starting with this, I have, let me check if I have the intermediate results, possibly. Well, okay, so let's start with the guesswork. So we guess the lowest mode shape. So the lowest mode shape is, of course, X1. The highest mode shape is X3 because it's a 3 degrees of freedom system. So the lowest mode shape would be X1, the highest mode shape would be X3. So X1, guess 1. So the bottom, the subscript is the mode shape number. The superscript is the guess number. So this is my first guess is, what do you think? Will they move all in phase or will they move out of phase? It's the lowest mode shape, so it's the easiest possible. So they will all be moving in phase. Now, do we choose 1, 1, 1? We can choose 1, 1, 1. That's definitely a perfectly reasonable choice, but we have a better choice. The better choice is to either look at the stiffnesses or look at the masses. If you look at the stiffness, you have that this is stiffer, so this mass will move less. This is less stiff, this mass will move a bit more. And this is even less stiff, this mass will move a bit more. And if you look at the inertias, they also give you the same story. This is 3I, so it's slower, it's more massive. This is 2I, this is I. So definitely this mass will be moving less than this and less than this, so on and so forth. So I would say, let's choose as a guess, instead of 1, 1, 1, let's choose 1/3, 1/2, and 1. Okay, so this is my first guess. I'll say 0.3, 0.51. Again, this is not a mistake, it's a guess. So whatever you put inside that will work. Even if you choose a completely unreasonable choice, after many iterations, you will still converge to the correct value, regardless of what your initial guess is. But if you make an informed guess, a good guess, you will need 1 or 2 iterations at most. Okay, so now that I have this, I can go inside this equation. Now this is given, this is guessed, this is guessed. So we can find directly how much this looks like this. So the idea is to look how much the left-hand side looks like the right-hand side, because they are equal, they should be equal. So let's check. So this matrix here is H times N. Times this guess equals a vector that is, I'll do it with MATLAB. Okay, so my guess X, guess 1, X1, guess 1 equals, it's a column vector of 0.3, 0.5, 1. So I have h times m times x1, guess 1. That's it, 0.9667. So 0.97, 1.97, and 2.97. And I'm arguing that this is equal to 1 over omega 1 squared, omega 1 because it's the lowest, omega, times x, and x was 0.3, 0.5, 1. Now I'm looking at this. How much is the left-hand side equal to the right-hand side? Well, first of all, they are the same up to a scale factor. So let's make one of them exactly equal. I can normalize, say, this one, which is the largest one, to look like 1. So normalizing I end up with 3 times 0.97. Let me normalize this with MATLAB very easily. So I do ounce divided by 3. I get 0.32, 0.66, and 0.99. Sorry, this should be what? Oh, it's not 3. Should be, sorry, this is my fault. This should be exactly 1. So I should divide this by ounce of 3. There you go. So this is 0.32. I'll say 33 because it's 5. So I'll round it up to 33. 66 is correct. And this is, of course, 1. So I have that if I take 2.97 out of this, I take 2.97 out of this, then this is 0.33, 0.66, 1. And then I end up with 1 over omega 1 squared times 0.3, 0.5, and 1. And now I can calculate the error. The error of course, no error on the last one. It's exactly 1. We made it 1, so there is no error. What is the error here? This is 0.33 minus 0.3 divided by 0.3. So 0.33. 0.33 minus 0.3 divided by 0.3. And this should be in brackets. Say times 100 to give a percentage. This is a 10% error, of course. And this is 0.66 minus 0.5 divided by 0.5. That's a 32% error. Okay, so we are still out of tolerance, definitely out of tolerance. We want 5% tolerance. If it's not given, assume 5% tolerance. Or 3 iterations, whatever is reached first. Okay, so this is greater than 5%. So continue. And now my new guess is this. This is now my new guess. Okay. So you start with this guess now. So I'll say that x1 guess 2 is 33, 66, and 1. And so we do it all over again. All over again means that I take this I copy, put it down, and then I copy this. I put it down here, and then I say that this is equal to, and this is equal to. So first of all, let me do this in MATLAB. Is x1 guess 2 equals 0.33, 0.66, and 1, and this is transposed. Okay, so I have h times m times x1 guess 2. This is what we get out of it. 1.10, 2.26, and 3.26. This is my left-hand side. And I argue that my left-hand side should look like 1 over omega 1 squared times the guess number 2, which is 0.33, 0.66, and 1. Now I look at this, and I ask myself how much the left-hand side looks like the right-hand side. So let me normalize. So this is iteration 2. This is iteration 1. If I normalize, that means I take the last vector, sorry, the last component out of the vector. So this is definitely 1. I take 3.26 out of it. So let me do this with MATLAB. I normalize this divided by ans 3. 0.34 and 0.69. Nice. Okay. That's equal to 0.33, 0.66, and 1. And so the error is of course 0% for the last one. And we have 69 minus 66 divided by 66, 4.45%. Nice. 4.5%. And for the first one, that's even smaller, of course, because it was smaller earlier. 34, 31, 33, 3%. So this is smaller than 5%. So I stop here, stop here. See, with a very good first guess, we only needed 2 iterations for convergence. Now that I stopped here, oh, sorry, this is not the same. This is equal to 1 over. Never forget this, because otherwise that's not an equality anymore. So now I'm arguing that if this is within 5% of this, that means that this is within 5% of this. Otherwise, they're not the same. Huh? If this is within 5% of this, this is within 5% of this. And so let's do that. 3.26 is almost equal to 1 over omega 1 squared. So how much is omega 1? Well, in that case, omega 1 is, oh, guys, I am always forgetting here that HM is I over K times this. So remember, I over K and I over K. So whatever we get here, we get I over K. So I over 3.26 I over K is almost equal to 1 over omega 1 squared. And so that means that omega 1 is equal to the square root of 3.26 k over I, sorry, 1 over 3.26 k over I. And this gives the square root of 1 over 3.26, the square root of 1 over 3.26, 0.5538, 0.55 times the square root of k over I. Because square root of k over I can't simplify, of course. Any questions? Is this easy? These marks at the exam gifted. Okay, these marks. I'm throwing marks at you. Okay, this is what I'm doing. So yeah, don't worry about it. Let's see what time is it. Let's say we start the highest one. Just start there. It's exactly the same. You just use a different equation, but it's exactly the same. So don't worry about it. We just start it there, and then I'll give you a break, and then we do the other part, which is the transverse vibration of beats. Online students, have you got any questions? You're so quiet. Why are you so quiet? I'm worried. You're so quiet. I'm worried. No. Okay. Hello, Ed. Okay. So let's start the other one. The other one is this one, highest. So I'll just copy this one all the way down. Now we find highest mode shape. So remember this is what we use. And in this case, the first guess would be, since it's the highest, we're talking about X3 now. So we are now looking at X3. Guess 1. Guess 3, sorry, X3, guess 1. They are all out of phase. And I argue they have the same issue as before. Okay, so the first one is slow and stiff. The last one is fast and compliant. So let's say 1. So I'll start with the same 0.3, 0.5, 1. But now with the added catch that they are out of phase. As much out of phase as possible. Okay, that means each mass is doing something opposite to its neighbors. This is as out of phase as a 3 degrees of freedom system can be. And again, it doesn't matter if you start with a negative or start with a positive, as long as they are out of phase, it's fine, because they are the same up to a scale factor. So m-1 times k, let me do this with MATLAB. m-1 times, oh, we did this already. Yes, is this. So this is m-1 times k. So this times this is do this with MATLAB, so it's m-1 times k, so it's the inverse of m times k. Okay, yes. So this thing times the first guess, so x3 guess 1 was 0.3, 0.5, and 1. So minus 0.5, so minus 0.5 and 1. So we have this times x3, yes, 1. Yeah. Now, I know for certain that some of you have created a code that does this automatically, okay? This is almost cheating, but it's not cheating because you have done it yourselves. I want to see intermediate steps. So if your code tells you intermediate steps, that's the same thing of what I'm doing. Okay, so up to you. I would not consider it as cheating, also because I have no way to check your computers anyway. So what's the point? So if you want, spend a bit of time to do some MATLAB code with the matrix iteration. Who knows? I mean, this is still your effort. See, you see what I mean? It's not cheating because it's something that you have spent time on, and you need to figure out how it works anyway. And so you're still learning. So I'm 100% on board with that. And imagine that last year, one of your colleagues in the MEQ said that I was being lazy because I was using MATLAB and Wolfram Alpha all the time instead of doing the calculations by hand. Okay. I mean, am I teaching maths? I don't think I'm teaching maths. I'm teaching a bit higher concepts, I believe. But that's okay. 0.83. Minus 1.55. And minus 1.5. Minus 1, no, 1.5. And this is equal to, now look at the equation is different, is omega squared times x. So this is omega 3 squared times x, which was guessed as 0.3 minus 0.5 and 1. Okay, so now I'm looking at this. And I ask myself, how different is the first one is the left-hand side from the right-hand side? So I'll do this with MATLAB again. Don't call me out if I do it with MATLAB. If I do this divided by ans 3, I would argue ans 2. I always like to divide by the largest one. The largest one is 1.55. So let's do that. So I have everything, all numbers are smaller than 1 or at most 1. And again, it doesn't matter which one you choose. It's always the same thing. So this left-hand side is minus 1.55 times. I will not take out the minus, so I'll take out just the positive 1.55. And this is 0.54, 1, and 0.96. Okay. Now you look at this, and well, see, this is a bit of a. I would probably like to keep using the last one because this is always 0. Now, if you start changing which one you normalize with, what happens that now your error gets more spread. It's still getting smaller, but it's now spread over 3 components rather than 2 only. So it's a bit harder to keep track of. So let's choose to make the last one 1. Okay, just to keep track of 2 numbers instead of 3 now. Again, it doesn't matter. It's the same thing, but now your error is spread over 3 elements rather than 2. So it's probably still best to divide by 1.5. So if I take 1.5 out, which is my third element here, and this is, let me do this again with MATLAB. So this is this, and I divide everything by ans 3 now. I get 0.56 minus 1.03 and 1. So I look at the error. And the error is, the error was here, this one. So the error is 56. And the previous one was 0.3 divided by 0.3, 86%. Ooh. You see, we are far away. Probably my guess wasn't very good. This one is minus 1.03. Minus 1.03. Minus minus becomes plus 0.5 divided by minus 0.5. This is 106%. And the last one is 0. Okay, so this is definitely greater than 5%. So continue. Okay, see, even if you get more than 100% error, don't be scared. If you just keep going, it will get smaller. It will always get smaller. 100% of the time, we'll always be getting smaller and smaller and smaller and smaller. Okay. Now, this guess arguably wasn't the best of the guesses. Okay. But again, it doesn't matter. Don't worry. At the exam, you only need 3 iterations, and then you can stop. At the end of your 3rd iteration, that's it. Whatever you got, you got. Okay. Well, if this was, imagine that this was almost the same, then the argument says that omega 3 squared is almost equal to 1.5. And of course, I'm forgetting here, because I'm always forgetting. You should never forget, but I can do that. K over I, it is there. So arguably, omega 3 squared is 1.5 K over I. Well, not in this case, because it's definitely not with this large of an error. But if you keep going, at some point, you'll get there. Okay, questions? No questions? Break? Yes, break. 5 minutes break. Yes.
Allora, nel tutorial quello su audio, loro fanno, li tengono uguali tutti e due. Se lei li ha invertiti.
Invertiti in che senso?
E lei ha fatto θ1 meno θ2 e θ2 meno θ1, invece loro le lasciano θ2 meno θ3.
Sì, ma hanno segno diverso.
Le frecce?
Sì, è la stessa cosa. No.
Invece nel suo...
Questa è oraria, questa è antioraria.
Nel suo invece...
Il mio invece vanno tutte nello stesso verso. È la stessa cosa. Sì, no. A me piace lasciare le frecce e invertire le parentesi perché so che vedi tutte queste cose. Questa è la seconda massa, quindi questo è θ2, θ2. Il primo è sempre la massa di cui stiamo parlando.
Quindi se la freccia è così... Sì.
Okay.
E poi quando lei fa... Sì, questa è qua, la guess. Lei ha fatto 1 diviso 2 e 1 diviso 3.
Sì.
E per il massimo però?
Sì, il massimo. Il massimo è 1.
No, però per trovare...
highest mi sa che ti conviene partire con 1 meno 1,
1. Sempre. E poi...
La West è più facile.
Sì. E poi nel... Posso fare una domanda già per quello dopo?
Yeah.
Praticamente in questo... In questa qua la seconda. Praticamente nel...
Ci arriviamo.
Esatto, praticamente loro fanno, allora loro tagliano la penultima, quindi qua, e L diviso 4 e 2 e invece loro usano praticamente questi due li hanno invertiti.
Sì, potrebbero essere sbagliati.
E questo è sbagliato sicuramente.
Sbagliato proprio. Poi lo guardiamo insieme. Lo facciamo insieme.
È la shape 2 invece che la shape 1.
Cominciamo con la prima, poi facciamo con la seconda.
Perfetto.
Asham asking, if we have a 4-degree of freedom system, there is no way to find mode shapes 2 and 3 using the iteration method alone. That is correct. You can only find the highest and the lowest. So if you have a 4-degree of freedom system, you'll find omega 1 and omega 4 and x1 and x4. To find 2 and 3, you will need the sweeping matrix method that we didn't talk about. So don't worry about that. And you need to find the second one, you can do the sweeping matrix method, and to find the third, you can use the orthogonality condition with 1, 2, and 4. You might say the mode shape 3 must be orthogonal to 1, 2, and 4, and so you have 3 equations. The 3 equations that you need to find the other one. Again, these methods that we are doing are the ones that were used when calculating things was expensive. So these iterative ways of doing it, it's because we want to avoid using a software, because there was no software. A few years ago only, a few decades ago, it would have seemed impossible. But we still needed a way to find mode shapes, and this was how you did it back in the olden days.
So the lowest mode shape, if we started with a guess of 1, we'll require more than 3 iterations.
Probably.
So in the exam, if we start from 1.1, we can just stop at 3 iterations. Okay, because starting from 1.1, it will get there of more than 100%. It won't reduce to less than 5%.
As long as you state, I'm stopping here. This is my third iteration. I stop here. I know that it's greater than 1. Then you calculate the error anyway. Then you say, okay, this is greater than 5%, but I'll stop here anyway. It's fine. Guys, next week is on Monday, is an unbelievably short lecture on phase plane method. It's literally 20 minutes lecture, then with an example, and that's also part of the exam. It's very easy. And then we'll do a dynamics review on Tuesday, which is exactly the same that we did for statics, solving past papers in 2 hours. For our coursework, the number of degrees of freedom depends on the number of nodes, right? Or is it 6 times the number of nodes? Is each node that depends on you. So if you use a model, an FE model will have so many degrees of freedom, and that would be the size of your mass and stiffness matrix for the FE model. Whereas for the experiment, we have discretized the structure with 19 degrees of freedom only. Ideally, we discretized it with 38 because it was 19 Z directions and 19 Y directions, but then we discarded all the Y directions, so effectively it's a 19 degrees of freedom system. But it doesn't mean that the experiment has 19 degrees of freedom. We observed 19 of them, but it's got infinitely many. Okay, guys, let's resume. I'll copy the table. I'll put it right here. So we can do the transverse vibration of beams. Transverse vibration of beams that is intimately connected to the whirling of shafts. Shafts, when they are driven at their critical speed, they'll deflect, they'll deform, and then you are creating an imbalance at that point, because the deformed shape of the shaft will start rotating all around. And so in that case, that means that you have, it's like creating an imbalance out of somewhere, out of nowhere, you create an imbalance. So this thing will, of course, be transmitted to the supports. And that means that your bearings will then have to provide dynamic reaction forces. So the action forces that are changing in time. And those are very taxing on the bearings. So your bearings will be worn out in no time if this keeps happening. Okay, so let's start with question 1, and we'll probably do just question 1, but both part A and part B. What is question 1? This one. See, what I was saying is that does it say? Well, no, it doesn't say. That's fine. So let's start with this one. Part 1. Let me copy this beam. So we have a fixed support on the left. A beam that is the same, it's divided in 3 equal segments. And we have one mass of 4m and one mass of 2m onto a shaft of EI and L divided by 3, L divided by 3, L divided by 3. Yeah, that's it. Yeah, that's it. So remember the direct stiffness method. Using the direct stiffness method is what we are using right now. So using direct stiffness method with the help of the table. Okay. We can find, first of all, we need to label the degrees of freedom. How many degrees of freedom do these masses have? The deflection, the deformation associated with a beam that is bending, it's 2 deformations per point. We have the deflection and the slope. In that case, we have x1 x2, x3, x4. Okay, these are the 4 degrees of freedom. So the stiffness matrix of this beam would be a 4 by 4. And so I can already start blueprinting my stiffness matrix. This will be 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This is my Planck stiffness matrix. I have no idea what these things are, but I can call them K11, K21, K31, K41, and so on and so forth. Okay, let me not call them that. Let's say these are blanks, but they know how to label. We know how to label them. So remember that Kij is deflection, so let's say displacement of degree of freedom I when degree of freedom J is forced. Okay, so it's the other way around. Sorry, why that is? I was thinking about this, the stiffness measure. This is the force in degree of freedom I when degree of freedom J is displaced. Apologies. Is displace unity. Because it's not just displaced because K is a stiffness, it's not a force. Okay, so let's do now. Let's displace one unit degree of freedom 1. This is 1 unit. This looks like, let me do this smaller. This is 1 unit. This looks like, the deformed shape of this beam looks like this. Okay, so what I have here is a fixed support. So now, assuming, well, it's not really assuming, it's imposing. Imposing that we have unit displacement in x1 and no other displacement in x2, x3, x4. That means that x2 and x4 are 0, and that creates effectively a fixed support here. We can now split this into 2 halves, where the left-hand side and the right-hand side look like, the left-hand side looks like this, and the right-hand side looks like this. You agree? Now you can just copy all the things that are here. And first, we need to check if this is A, B, or C. Now, this is unit displacement. Unit displacement, let me draw it here. This is displacement. So let's call it deflection. And this is slope. Deflection. And this is slope. But also in A, we have fixed support. And in B, we have fixed support. And here we have pin in C and pin in D. So see, it's quite easy to identify what we have based on the kind of deformation we have and the kind of support we have. Now, in this case, we have unit displacement and fixed support. And that means we are looking at A on the left, and we have unit displacement and fixed support. We are also looking at A on the right. So it's A on the left, A on the right. This is A and A. So I can just copy all the forces that appear in A, forces and moments. So it's P and M, so it's P on the left. It's M on the left. Then we have M on the left and P on the left. So P on the left looks like this, and M on the left looks like this. On the right, it's exactly equal and opposite. Yes. So we have P right, M right, M right, and P right. Okay, so now what do we want? We want, since we are imposing x1 is 1, we are finding, with this thing, we find ki1. Okay, this is what we are finding. We are finding all the k's of the first column. So I can say that k11 equals, then k21 equals, k31 equals, and k41 equals. So let's look at k11. K11 is the force in degree of freedom 1 when degree of freedom 1 is displaced 1 unit. So degree of freedom 1 is this. What is the force in degree of freedom 1? It's PL plus PR. Can you see it? PL plus PR. And this is equal to PL is 12 VI over L cubed. Also, remember these, 12 VI over L divided by 3 cubed plus exactly the same. See, on the right, it's exactly 12 VI over L cubed. And this is equal to, let me see if I have the solution. I do have the solution. That would be, no, this is not this. It's the other one. Well, we'll have to find this. This is 27. So it's 27 times 12. How much is it? 27 times 12, 27 times 12. It's 324. 324 times 2. 648. So this should be 648 EI over L cubed. Do you agree? Yeah, no? Yeah, no, no? Okay, I was looking for vital signs from the classrooms. Okay, 648 EI over L cubed. Let's look at K21. K21 is the second degree of freedom, which is this one. So this one is minus PR. Minus because X2 is down, PR is up. So they are against each other. So this is minus PR. And this is 12 times 27. How much was that? 324. So it's minus 324. So let me do this, minus 12 EI over L divided by 3 cubed is minus 324 EI over L cubed. Okay, this is the first And this is the second, this is K11, this is K21. Let's look at K31. K31 is the third degree of freedom, is this one, and this one is MR minus ML. This is MR minus ML. And they are exactly the same because they come from the same table. They are equal and opposite. And also EIL divided by 3, EIL divided by 3. So of course, this will give me 0, but let me do it properly. So this is 6EI over L squared, 6EI over L divided by 3 squared minus 6EI over L divided by 3 squared equal 0. Okay. And K41 is just MR. I can see that easily. This is X4, this is MR. And so that's just equal to 9 times 6, 54. So it's minus 54 EI over L squared. Okay. Now I can just go in my big matrix and put all these numbers in. So let me take this out. So I'll take EI over L cubed out. And then this is 648. This is minus 324 L. No, this is minus 324. This is 0. And this is 54 L. Okay? Does it make sense? Good. Now I'll do it completely arbitrary. You should do this one by one, column by column. But in the exam, I will not be asking you for all the columns. I will be asking you, say, like in this case, let's find K34. How do you find K34? So let's say I want to find this one here, this element. Because at the exam, that's what I'm asking. I'm asking for one or more elements. How do you do that? Well, first of all, remember that whatever we put on the column, we also put on the rows. Because when you do it, you might find other elements that I'm asking you for. And now to find K34, which is this one, I need to, that's the fourth column. So I need to rotate X4. So to find K34, I impose X equals this, all zeros and 1. And then I look at the beam again. I look at the beam and then I impose this unit rotation here. That means I put a screwdriver and I rotate in the direction of X4 1 radian. And this gives me, since X1 and X3 are 0, this effectively gives me fixed support here. And so this gives me a beam that cannot slope here, and goes down, and then goes in. Can you see it? So there must be no slope here because it's a fixed support, but here there can be a slope because it's a pin. So pin, that definitely allows for a slope. All right, so Now that we have this, we can split this into halves. And we have the left and the right parts. If I look at it, this looks to me like this table. And this looks to me like this. And so of course, if we go up here, we are now talking about slope. So it's either B or D. And on the left, we have a fixed support. So it's B. On the right, we have a pin. So it's D. So it's B on the left and D on the right. You have B on the left and D on the right. So for B, I have to copy P and P, M1, M2. So it should be P down, P up, M1, like this. I forgot. Let me copy this table. There you go. So I'm copying here P up, P down, and then M1 clockwise, not counterclockwise. So M1 clockwise. This is M1 on the left. And this is M2 clockwise. This is M2 on the left. On D, instead, I'm copying P and M. So P goes like this. This is PR. P goes like that. This is PR. And the moment is only here, and it goes like this. MR. Okay. I'll get rid of the table. And so I want K34. So K34 is this one. So K34 is M2L. In this case, K34 is M2L, which is, I got rid of the table. M2L is 2EI over L. This case is on the left, we have EI is EI, but L is L divided by 3. So it's 2EI over L divided by 3, which is 6EI over L. This is K34. Okay? So this is how you do it, element by element. You don't need to find all the elements. You can also spot the element that you want. And at the exam, that's exactly what I'm asking you to do. Now, instead of finding the entire column, just find K13. So find K13, and then I can ask you K11, K12, K13, K31. But if you find K13, you have also found K31, so you don't need to redo the entire process again. You can just say by symmetry, found K13, found K31. Again, these more marks that I'm throwing you. Okay? Questions on this? No questions? Probably yes.
If we get K13 wrong in the exam, and then you ask us to find K31, and we put in what we found for K13.
That's still correct. So you still get partial marks, because the fact that you say K31 is the same as K13 by symmetry, this is correct. Now the fact that you got K13 wrong, it's another mistake. Okay, that's fine. All right. Any more questions? No? No? So let's check one that is a bit more complicated, because I want the ones with the EIs that are already this one. See, because we have the EI is different here, the L divided by 4 is different here. So let's do this one. Probably covers, or even this one. This one has 6 degrees of freedom. Ooh, 6 degrees of freedom. I like this. It's 4EI, 3EI over L over 2L. See, 4EI. Guys, this is the main source of mistakes. The fact that you don't realize that it's 4EI and 3i, what's on the left, what's on the right. This is the greatest source of mistakes for this part of the exam. So if you practice a bit, it's going to be very easy. Just need to practice a little bit. Okay, so which one do you want to do? This 6 degrees of freedom one or the easier, this one? So Alessandro was saying that this one probably has the solution wrong.
Just one thing. Yeah.
Just one thing is wrong. So which one was that?
It was 3, 4, and 3, 3. Well, 3, 4, 3.
K34. So let's find K34 of this thing here. So just very spot. I want one element of this stiffness matrix. So let me copy the beam first. This is question 2. Well, it's question 1, 1B, whatever. So apparently Alessandro has spotted a mistake in the official solution of this beam. So let's check who is right. We have 2, 4, 2. So 3. X and 3. So we have L divided by 4, L divided by 2, L divided by 4. And then we have 2 EI, EI, and 2 E. And we have 3M and 2M. Of course, the masses are not used because we are just finding the stiffness. But if I ask you to find the natural frequencies of this, you need to form the mass matrix. You have the stiffness matrix for forming mass matrix. So that's why 3M and 2M are important. But if I ask to find the stiffness only, we don't care about the masses. Okay, so we say, let's find K34, so?
Yeah.
K34. And I believe that these are labeled in the same way. So this is X1,
Yeah.
this is X2, this is X3, and this one is X4. Okay, so if you want to find K34, I'll take this and I'll assume, so impose X. Which one? Which one? The fourth one. So 0, 0, 0, 1. That means imposing this. Imposing this means that this thing is completely fixed because X1 and X3 are 0. So this goes, this is X4 is unit. So this is like that. So I have something like this. Okay, remember, look at this. This has no slope on the left and also no slope on the right. Ah, so complicated. There you go. That's the best I can do. Okay. All right. So let me split this into left and right.
Is it not X3 equal to 1?
What X3 equal to 1? No, it's X4. Well, it depends. If you want to find K43, which is the same thing, okay, you can, I mean, it depends on what you're finding. So this is right, as I said. And so on the left, this looks like I'd argue that this is B. And you let me know if this is right or not. And on the right, I also argue that this is B. Okay, so B on the left and B on the right. Let me copy. So B on the left, this looks like this. So I have M2L. PL. PL. And then 1L. And so on the other way, I also have M1L. Well, let me copy the other one then. Don't need this anymore. For this one, I have M1L. So both clockwise. PR. This is clockwise M1R. Clockwise M2R and PR. Okay. So we are interested in K34, which is this one, but X3 is exactly M2L. So I argue that K34 is M2L, which is equal to, you check the table, M2L is 2EI over L. So we have 2. See, we have EI, it's 2EI over L divided by 2. And this is 4EI over L. Is this correct, Alessandro?
I found 8.
You found what?
8.
8. How did you find 8?
Because
What does the solution say?
says 4.
Ha. So the solution is correct, or at least I got the same as the solution. How did you get 8?
We do the counts.
Yes.
I did it for 3, so mine's slightly different.
Shall we do it for 3? So let's find that K34, and I argue that K34 is this. Now let's find K43, which should be exactly the same. But we need to redo. So let's find K43 that we know it's equal to K34. K43, yeah, is equal to K34, but now imposing X equals 0, 0, 1, 0. Now, if I impose 0, 0, 1, 0 to this one, now I'm using this one. And this is my fixed support. And so I have small here and something like this.
I found my mistake.
Ah, you found your mistake, Alessandro. Very good. Well, I'll do it regardless, just to prove you undoubtedly wrong. Okay. So we have on the left, we have B, because it's a fixed support with slope. On the right, we also have B, because it's another fixed support with slope. And so I'll just copy these ones again. Now, of course, I must copy them correctly because one is shorter than the other. This one is shorter. And this one is longer. But I still have the same M2L, PL, PL, M1L. And then I have PR, M1R, PR, M2R, and I can get rid of these. And now K43 is K43 is this. And this is M2R. And M2R is M2, 2EI over L. But in this case, we have 2EI over, no, it's not this. It's 2EI over L divided by 2. It's 2EI is equal to 4EI over L. Sorry, Alessandro. Okay, so the solution was correct. And of course, we have also proven that K34 is equal to K43. This is exactly the same thing. Okay, any more questions? No? Online students, all good?
So whenever we have a force is equal to fix, the force is equal to.
When you have a deformation like that, the forces that arise in the beam, they are exactly those.
One would put, let's say, x1 equal to 0. Then it becomes fixed.
Yeah.
Always.
Yeah, always, because that's effectively what it is. If you impose that x1 is 0, you are fixing it. That's by design. Yes.
How do you do it? You know how it's 2EI or EI?
Yeah. Well, in this case, see, if I wanted to find K33, let's find K33. To find K33, I argue that this is M1L plus M1R. This is M1L plus M1R. And this gives me M1L, M1 in the table is 4EI over L. So in this case is 4 times, on the left, EI is 2EI. So it's 4 2EI over L plus M1R. Sorry, it's L divided by 4. Okay, see what I'm doing? I'm using all the things that are on the left. Should be 4 EI over L, but EI is 2 EI and L is L divided by 4. Plus on the right, we have 4 EI over L divided by 2. Okay, because on the right, I have EI and L divided by 2. So this is 8 times 4 is 32. So this gives me 32 EI over L plus 8 EI over L. So this gives me in the end 40 EI over L. Okay, so in the end you get this one for K33. Any questions? Now, not required for the exam, but let's have a look at this thing here. This is, remember, this is the model order reduction that we did last time. Say, in order to find this K star, which is the reduced stiffness matrix of this system, this was taken by, remember, D minus F E minus 1 times F transposed. Okay, again, this is just so if you want to solve the entire tutorial sheet, you also need to remember the other equation that we gave at the end of the lecture. At the exam, I will not be bothering with this because it's just a block matrix multiplication, which is very long and it will not add much to the exam. So I will never be giving you anything like that at the exam for model order reduction. Okay. It's 45 past. Any questions? No? See, this is very easy. This is one of the easiest parts of the exam. Can we email you to find the correct solution for coursework A? What do you mean the correct? So, oh, you want the numbers? I'm not comfortable with the numbers. But yeah, email me anyway, and I'll tell you who your marker is, and they can tell you where you got it wrong. Okay. Ashram. One thing that I want to say, oh, remember that the questions at the exam for dynamics, they are mixed in a different way. So we have transverse vibration of beams and model analysis in the same question. And the other question is vibration absorbers and phase plane analysis, which is what we are doing next week, phase plane analysis, okay? So we are not done yet. Last lecture left. And good luck. Good luck. Come on, guys. Go study for coursework B, as it's a bit intensive. I'm going to stop recording here.